All right, today we are diving into an invisible force that shapes, well, pretty much everything around us, from the tiniest medical implants inside our bodies to the massive rockets reaching for the stars. We are talking about mechanical engineering. So let me start by asking you a question. What do you think self-driving cars, life-saving medical devices, and those incredible rovers on Mars all have in common? What is the secret ingredient, that hidden engine, driving all of this amazing technology?
Well, the answer is mechanical engineering. It's the fundamental discipline that makes all of them possible. And what's so cool is that this is a field with truly ancient roots, but at the same time, it's more critical than ever for building our future.
Okay, so to really get a grip on its power, we have to start with the absolute basics. What exactly is mechanical engineering?
You can really boil it down to this. It's the art and science of anything that moves. Seriously, if a machine has moving parts or if a structure is designed to handle some kind of immense force, you can bet a mechanical engineer was involved. They're the ones who take the fundamental laws of the universe and use them to build actual real-world solutions.
But before you can jump in and design the next-generation jet engine or a life-saving prosthetic limb, you first have to master the fundamental language of the universe. And believe me, that language is written with physics and math. You see, engineering demands just incredible precision. For instance, it's not enough to say a car is going 60 miles per hour. That's just a scalar. An engineer needs the vector, 60 miles per hour times heading north. That tiny distinction between just a magnitude and a magnitude with direction is everything. Get it wrong and whoops, your satellite might miss its target by millions of miles.
And then there's this. This is one of the absolute cornerstones of the entire field. Force equals mass times acceleration. Newton's second law. It looks so simple, right? But this little equation is basically the master rulebook for how things move. It governs everything, from the combustion happening inside an engine to the orbit of a satellite.
And this brings us to a really crucial point about being an engineer. Math isn't about memorizing a bunch of formulas. It's a way of thinking. It's about really getting the why behind the basics, so you can take a massive, complicated problem like, say, a skyscraper's entire ventilation system and break it down into smaller, solvable pieces.
So, how exactly are these foundational principles of physics and math forged into a practical, hands-on toolkit? Well, that whole journey happens inside the engineering curriculum.
To build out that toolkit, every mechanical engineering student has to master these core subjects. Each one gives you a totally unique lens for solving a very specific kind of physical problem, from things that are supposed to stand perfectly still to things that move at unbelievable speeds.
First up is statics, which is the physics of things that don't move. Now, think about a massive bridge. Statics is how engineers calculate every single force acting on that bridge. Its own incredible weight, the weight of thousands of cars, the constant push of the wind, all to make sure it remains perfectly still and perfectly safe. Then you've got dynamics, which is the complete opposite. It's the study of things that are in motion. This is basically your high school physics class on steroids. It's used to analyze everything from the incredibly complex dance of pistons inside a car engine to the super precise trajectory of a satellite orbiting Earth.
Now, sometimes the forces of nature are a little more powerful than we expect. Back in 1940, the Tacoma Narrows Bridge famously just twisted itself apart in what seemed like a pretty gentle wind. The cause? Uncontrolled vibrations that just kept building on each other.
And this disaster, as tragic as it was, perfectly illustrates why engineers have to study vibrations analysis. That failure taught us a critical lesson. Now, engineers analyze vibrations in everything, planes, buildings, even satellites, to make absolutely sure a system can handle the stresses it's going to face and prevent that kind of catastrophic failure. Every failure becomes a lesson that makes the next design even stronger.
Okay, so we've seen the theory, we've been in the classroom, now for the really exciting part. Let's look at how this powerful toolkit is actually used to build and innovate out in the real world.
This field has such an incredible legacy. It started thousands of years ago with simple but brilliant machines like the lever and the wheel. It literally powered the Industrial Revolution with a steam engine, and today it's pushing the absolute boundaries of what's possible with cutting-edge fields like mechatronics and nanotechnology.
And the field today is just unbelievably diverse. For example, you could specialize in mechatronics, where you're blending mechanics, electronics, and software to create intelligent systems like industrial robots. Or you could dive into biomechanics, applying engineering principles to the human body to design revolutionary prosthetic limbs. Or you could even work with composites, inventing entirely new materials like the ultralight carbon fiber that makes modern aircraft and spacecraft possible.
And the innovation just never stops. Researchers are tackling these huge, monumental challenges. At MIT, for instance, they're creating these new polymer coatings to make bridges practically corrosion-proof, while at the same time, they're chasing one of engineering's biggest holy grails, a superconductor that works at room temperature. I mean, that would completely revolutionize our entire energy grid.
So, think about that. We've gone from a single, simple equation, F equals ma, all the way to some of the most complex machines and materials ever created. Let's bring it all together.
So, at the end of the day, this is what a mechanical engineer does. They are, first and foremost, problem solvers. They analyze a need, they design a solution using incredibly powerful software, they build and test prototypes to make sure it actually works, and then they oversee the manufacturing process that brings that solution to the entire world.
So, from ancient levers to modern robotics, mechanical engineering is all about turning scientific principles into reality. The laws of physics, those are constant, but the challenges we face, they're always new. So the only question left is, what will we build next?